this is Dr. Asan Abdullah with the course Deep Reinforcement Learning. The topic which we are covering is regularization, which is the fifth topic. And this topic is divided into further subtopics. And this subtopic is 5B, which is slightly more than the basic concepts which were covered in the topic 5A. And this video, like other videos, is developed using the personalized learning management system available at www.pgmcq.com/Google, which is the supplemental material for this video. So the approach which we have adopted in this course is content delivery. And this content delivery is used by the leading learning management systems. And it has certain wonderful features. And there are millions of users of learning management systems which are based on content delivery. And here are some of the features which are there in such systems. You can read through them and go through them. And these are the 6 features uh, which are used in the personalized learning management system, which are, for example, full scale text search, and based upon that text search, the Q&A of interest can be retrieved. Then it supports people who are visually handicapped, and it supports working in a small space to view, such as a smartphone, and the progress is tracked of the end user. And of course, there is MCQ based online testing and evaluation system, and so on. So there is a link here in the blue color, which is the link to these videos which show you how to use that learning management system, for which the link is shown in green. And there are two basically approaches. One is the question and answer or Q&A based approach, and then is the traditional learning based approach. So the approach which we have adapted or adopted in this course is a combination of both. So Q&A is proactive, it is engaging, and it adapts to the user requirements, and of course it promotes thinking. And machines are not good at thinking, so we are ahead of them. It promotes that. So this is a blend of these two technologies, the approach or the methodology which we have been using in this course and other courses. So this is the breakdown of the topics which are covered in this course, Deep Reinforcement Learning. And right now we are at the fifth topic, which is regularization. Within that topic, there are 15 questions and answers, and every question and answer is a concept. And these Q&As are divided into 4 subtopics: 5A, which you can see is in yellow color, and 5B, 5C, and 5D in different colors. So we go through each of them as per their difficulty. And without further ado, we move on to the details of the Q&A for this video lecture. So we see how regularization in deep learning is different from regularization in reinforcement learning. So we are at topic number 5A, which is regularization. And as a matter of fact, it is A2 because we're starting from question number 3. So how regularization in deep learning different from regularization in reinforcement learning? Now we know that what is regularization, right? This is a fundamental concept of machine learning. This is all about generalization. Machine learning is generalization, right? If there is no generalization, there is no machine learning, right? And generalization is with reduction in overfitting. If it's overfitting, then it's not machine. This is like memorization. Now, while, for example, let's look at it. So while I'll discuss this diagram with you. So while both deep learning and reinforcement learning incorporate use regularization, but their goals, their context, their techniques, their applications, they're quite different because of the unique nature of the paradigm. This is visible from here. Okay, I'll discuss this. And in deep learning, right? In deep learning, regularization, okay, addresses overfitting, right? So we have this pictures of dogs, and we have this label data set. We have pictures of cats, okay, and we have this classifier, and we would like to identify the picture as a picture of a dog or a cat, okay. So the solution basically is deep neural network, right? This is the sample features. This is the label guess, and these are the different weights and these different activities of the neurons, color coded, right? And so in deep learning, basically we are looking at overfitting during the supervised learning tasks. So we have this fixed data set available. So we have these techniques like L1, L2, which we have discussed, dropout, early stopping, they're applied. And they're applied directly to this neural network, right? During the training process and to prevent this neural network from memorizing the training data. So this is how it works. We've discussed this. This we'll be discussing in classical reinforcement learning. What we have this agent and we have this environment, and the agent takes actions, and with the or the agent interacts with the environment through the actions, and then there are observations, and then there are rewards also, there are penalties also, and those actions basically are they are reflect those the impact of the observations and rewards is reflected in these actions. Okay, so the agent learns by interactions. There is no kind of that labeled data, and the objective is to maximize the long term cumulative rewards, expected future reward, expected. Like say for example, there's a game of football, right? And one team has scored a goal and the other has not scored a goal, so we know that which team is winning at this point in time, right? At this point in time, of course, when the game the finish the time is over, then of course if that lead was there, then one team has won. But in reinforcement learning, expected future reward, so the reward is not there. The end will determine whether the what was the reward or what it was not there. So maximize the long-term cumulative rewards. Long-term rewards, they're different. So over here, overfitting is more of a policy overfitting. Policy we have discussed, we'll discuss more. So the agent performs in a training environment, okay, but poorly in the unseen or slightly varied environment. So this agent learns through the actions at that training environment, but when it is taken to a different environment or slightly variation in the environment, okay, then it doesn't perform well. So regularization in reinforcement learning focuses on stabilizing the learning, okay, and rather than just parameter smoothing, because this is almost interactive. This could be in real time also. This is not the case over here in classical deep learning. So we have one thing more here, which is deep reinforcement learning. Deep reinforcement learning is that this agent is replaced by the neural network or by the deep learning network, okay, and then so we have the best of the both worlds. All right, so let's go to the bullets. So the objective function, what is the objective function? Okay, in deep learning, okay, regularization modifies the loss function, and reduces the overfitting in the label data, right? And that loss function is modified by virtue of traversing by the in that loss space also. But in reinforcement learning, okay, there is an adjustment of the reward function or policy loss, okay, to stabilize the learning, right? And in reinforcement learning, the objectives are dynamic because things are happening, things are changing. So the way you have a robot or you have a self-driven car, so that's dynamic and depend on the environment interaction. So when the vehicle is driving, there may be people crossing the road, there could be other vehicles, there could be traffic signals. So that vehicle has to interact with the environment. So the regularization for for reinforcement learning is more context sensitive. It's more, so there's a big difference. Then is the learning paradigm. Learning paradigm, deep learning is basically supervised learning. The data is static, the labels are also static. A picture of a dog will always remain the picture of a dog. But for a self-driven car, the position of the car is changing. The even if the car has stopped, maybe there are people crossing the road or other vehicles or maybe something else. So reinforcement learning involves agents learning from the sequential experiences, interactive experiences, and the delayed rewards. So don't get worried about what is meant by delayed rewards because there's a whole topic on reinforcement learning. So because of of these differences, reinforcement learning is prone to overfitting. It's prone to affected by the environment dynamics. So it needs those regularization methods that are temporal, that are dependent upon time, right? And of course, it involves exploration also. So very different from deep learning, but regularization is there. So I use the word exploration. So what is the difference between exploration, or how exploration goes versus generalization? Regularization in deep learning basically improves generalization for the unseen data, unlabeled data. However, in reinforcement learning, okay, there has to be a balance between exploration and exploitation. Okay, exploration is finding something, and exploitation is making use of it. So this we will cover in detail, but there is a big difference between exploration and generalization. So in reinforcement learning, we have techniques like which are different from deep learning. Okay, and which kind of avoid suboptimal strategies also. Okay, and why this is why a strategy can be suboptimal because of insufficient exploration. Then is the regularization techniques. So in deep learning, we have L1, we have L2 regularization, we have dropout, data augmentation. We have covered this. But in reinforcement learning, there are techniques which we will cover, but they affect the reward. Okay, and the techniques of deep learning cannot be used in reinforcement learning, such as dropout, because that may be harmful, because that could introduce instability in the feedback loop, and so on. We cannot use them. So, and the stability needs. Deep learning models which are static, okay, static in the sense that the data does not changes, the label, the data doesn't changes. So, because that are the static training data, they can tolerate instability. However, for reinforcement learning, is highly sensitive to instability due to the nature of the environment feedback. So, for reinforcement learning, regularization targets stability, such as preventing the collapse of the system also. So, if it sounds complicated, you don't have to worry, because we have just touched upon reinforcement learning, and there are several topics on reinforcement learning. So, when we discussed the regularization techniques, so we talked about L1 and L2 regularization. So how do they differ? And when should each be used? Okay. And when should each be used? So it depends upon the type of penalty. Then there is the significance of the behavior of the weight. And of course, the use cases also. You cannot use them anywhere and everywhere. So basically, I'll explain this diagram to you also. So these two techniques are they of course they are used to reduce overfitting, and of course the purpose is to improve the model generalization, and this is achieved, as we discussed before, by adding a penalty term to the loss function. But the difference between L1 and L2, the fundamental difference is how they penalize the weights of a model. Okay, so that we touched upon. So let's go into some details. Okay, the type of penalty. Type of penalty, L1 regularization adds the absolute values of the weights. Absolute values of the weights, okay, to the loss function, while L2 adds the squared values. So L1 creates a linear penalty that encourages a zero weight. So you can see the linearity over here. Linear penalty, right? And L2 creates a quadratic penalty. You can see the quadratic here, quadratic penalty that discourage large weights but retains all the features, right? So you see that the features are retained. Over here it is everything is not retained, right? Because this is this is a circle, right? These things are quadratic. Recall the equation of a circle, which is also quadratic. So then is the weight behavior. Weight behavior, so it tends to push the weights to zero. Okay, L1 tends to push some weights exactly to zero. So those so whatever is pushed to 0, that is gone from the model. So this is kind of sudden, while L2 regularization shrinks weight smoothly towards 0, so this is more smooth, and that is not very smooth, as you can see from the picture here also, right? And so L2 is more stable. Why? Because it works smoothly and it's continuous. So while L1 produces sparse weight distributions. Okay, and then is the model interpretability. So L1 is results into simpler, more interpretable models. Okay, by only selecting the relevant features. So this is good for scenarios where we are looking at feature selection or explanation. So L2 includes all features with reduced influences. So remember that for L2, the weights are reduced, but they are hardly set to 0. But in L1, the weights can be 0. It means that that feature is gone. So L2 includes all features with reduced influence, which may lower the interpretability, right? But maintain completeness. All the features are there. But in L1, all the features are not there. So because of L1, since the weight assigned can be 0, that promotes sparsity. So that makes the model lighter because some features are taken out, and it is easier to analyze, right? But less stable with noisy data. This is the empirical results. Now L2 basically, since it retains the feature but with lower weight, has greater stability, and it has the smoothing and the optimizing, and of course there are minor data fluctuations. So when we have higher dimensional space, then L2 is a better choice. And finally, the use cases for L1 and L2. Okay. So L1, when feature selection or model simplicity is important. Keep this feature, do not keep this feature. So when we have high dimensional sparse data sets, right? Now L2 for tasks needing stability with smooth gradients, such as deep networks. Okay. Or of course, when all input features contribute, all features versus some features as in L1 contribute, maybe the strength is less, but contribute meaningfully. Okay. So that's for the, and of course, as before, if things are not clear, I would suggest that you read about model interpretability and weight behavior. Okay. So the details are given here. And if you are still not satisfied, so there is more reading material. All right. So finally, we are coming towards the end of this video. So what is dropout and how does it help prevent overfitting? So dropout, as you can see here, so there's a random deactivation of some of the neurons. So if of course it's a regularization technique, and of course the purpose is to prevent overfitting, and randomly dropping out or deactivating a fraction of the neurons during each training iteration. So some of the neurons were removed. This means that what does this mean? That at each training step we have a different subset of neurons. Some are added, some are removed. Okay, and of course not only the neuron is removed, but its corresponding connections are also removed. So the objective or the end result is that the network does not only rely on a single neuron. Okay, but so it becomes robust because it is relying on different neurons. So as a consequence, it is less sensitive to certain samples. As a consequence, generalization increases. As a consequence, memorization decreases. Okay, right? So of course, let's move on to model averaging. So this we have covered model averaging. So what is model averaging? So when we train different subnetwork, this is a subnetwork, and there can be if other neurons are removed, there could be a different subnetwork. So we have training of different subnetworks on each batch due to dropout. So we have the final model like is an ensemble of many networks, collection of many networks. So as a consequence, we have this ensemble, and we have an average generalization. So as a consequence of that average generalization, the risk of overfitting is reduced because it is not dependent on or relying on fixed or the same neurons. So, what is the regularization effect? Basically, this dropout or randomly turning off uh, the neurons, okay, that basically injects noise into the network during training. So, what is the consequence of this noise is that overconfident predictions, right, or which are highly sensitive to particular patterns, okay, they are discouraged. And what is promoted is smoother and more generalized mappings from the input to the output. That's the consequence. That's the effect of regularization. And what is reduced co-adaptation? That is that when you are randomly dropping the neurons, okay. So when the neurons are randomly dropped, okay, so this reduces co-adaptation. What is co-adaptation? When neurons rely too heavily on each other, so they start working kind of independently. So that results into more robust and diverse feature extraction across the network because they are not dependent upon the neighboring neurons, right? So that makes it more robust. All right. So that robustness basically can handle noisy data also. And training the robustness. So this is what I was saying. The dropout encourages the model to become resilient to missing or corrupted data, which is a reality, like the internet. So internet was meant to sustain attacks on the network, right? So that is it's very fail safe. So if part of the network is destroyed, the traffic is routed over some other part of the network, right? The same is true over here. So we train the network to become resilient to missing or corrupted data. Now, since the neural network is a network, internet is also a network. Since neurons can depend upon, so they are not relying on certain neurons to be active always, okay, because of the dropout. So that results into training in robustness. Therefore, the network becomes fault tolerant, like internet, leading to better performance for what? For noisy data, better performance for unseen examples. It means that better generalization. That is better generalization. Okay, so let me zoom here. So this is basically at the training time, right? This is without dropout, right? So this is present with a certain probability. Okay, at the training time. At the training time, it is present with a certain probability, and at the test time, it is present, right? So this is what we have the standard neural network, and this is the one which we have is the so 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So these neurons were removed along with their connections. So this is standard neural network, and this is the after applying the dropout. So at the time of training, we remove the neurons, right? And it gets trained, and this neuron is spread with a certain probability. And then, of course, it is at the test time it is present. So that's all for this subtopic. Thank you.